went through a couple of different ideas in terms of proof methods. The next one is proof by cases or division of cases, essentially same exact idea. The reason we do this is sometimes it's easier to actually prove anything, not just a theorem, is you break it down into different cases or different ideas, and then you prove each one separately. Once you've proved them all separately, it's much easier to combine it together and say that it all works together. So let's say I want to show that P implies Q, P1 implies P2, implies Q. We use the tautology for that, where P1, the whole P, whatever theory we have of implies Q, if and only if P1 implies Q, P2 implies Q, and it's a conjunction. So P1 implies Q and P2 implies Q, and so on, so on, so on. So you've taken them, broken them all together, and then broken them all out separately, and then combined them together in an AND statement, where you say it's an exhaustive proof in which all cases are considered, and now it's a proof by cases. So you're just breaking everything down. So let's say I have a theorem where if n is an integer, then n square is greater than or equal to n. In terms of proof by cases, what we're going to do is case 1, where n equal to 0, 0 square is equal to 0. Second case is n is greater than 0. So essentially n is greater than 1, greater than or equal to 1. We need to get n square greater than or equal to n, since we can multiply both sides of the inequality by n, which is positive again. So long as we're keeping it positive, it's simple as that. The third case scenario is n is less than 0. So now n square, although it's less than 0, n square has to be greater than or equal to 0, since we can again multiply both sides of the inequality by n. And it's going to be negative, so it kind of changes the sign of the inequality. In this case, we then end up with n square is greater than or equal to 0 is greater than or equal to n, because your n is negative. And so n square becomes greater than or equal to n again. So we proved it for all three cases where it could be 0, greater than 0, or less than 0. And we kind of showed that inequality to come around the same in that case scenario. So this is essentially your proof by cases. Another example is, let's say n is equal to z. In that case scenario, we need to prove that 9n square plus 3n minus 2 is even. Now we have 9n square plus 3n minus 2, which can be broken down into 3n plus 2 multiplied by 3n minus 1. We know that n is an integer at this point. So which implies that 3n plus 2 multiplied by 3n minus 1 is a product of two different integers. So we have two different case scenarios that we can play with. One, that it is even, and second, that it's odd. If it's odd, essentially that's the failure of the statement itself. We need to prove that it is even. So for the first case, 9n square plus 3n minus 2, it's trivial because although it's the product of two integers, one of which is even. So it is essentially even. If you do 3n plus 2 is odd, then it implies that 3n plus 2 minus 3 is even, which implies that 3n minus 1 is even, because it's the second side of the second bracket essentially, or parenthesis, which implies that 3n square plus 3n, 9n square plus 3n minus 2 is even. Again, because one of the factors is even, you've broken it down and you've kind of proved the second case to be true as well. So again, proof by cases is just a situation where you're going to take each case, work off of it separately, and then basically define that the statement is true based on the fact that all cases are true. And that's everything to do with proof by cases. Thank you.